welcome you all in the fifth lecture of Electronics Measurement and Instrumentation. In this lecture, I will discuss the electronics voltmeters that are used for the measurement of alternating current, that is AC current. So, I Dr. Indu Prabha Singh from Shri Ram Swarup Memorial College of Engineering and Management is here to discuss the electronics voltmeter that are used for the AC signal measurement. So, in this lecture I will discuss the AC electronics voltmeter, that is representing the average value of the AC signal. Then I will discuss the peak responding voltmeter, that will show the peak value of the input voltage, and then RMS responding voltmeter, that means the meter that we are using same PMMC instrument for all this, but it will show the value of RMS value, the true RMS value of the input signal. Then we will use a current measurement with electronics instrument. So, for the AC measurement, when we want to measure AC signal, then we need basically to convert that AC signal into DC signal. So, for this we need AC to DC converter, because our PMMC instrument only measures the DC current. So, we have to convert the AC signal into DC signal. So, for this purpose we can use only a single diode for this purpose. So, suppose we are using a diode. So, we can use a diode. Suppose we want to measure a signal. So, we have that signal, input signal. Suppose this is the input signal whose amplitude we want to measure. Then this is we will connect a diode. Then we will use a PMMC instrument. So, what will happen? This diode will convert AC signal into DC signal, because diode will conduct only when anode is positive with respect to cathode. So, when this positive cycle appears, this diode anode is positive with respect to cathode, and so diode will conduct, and so in this meter the positive amplitude will appear. In negative portion of the signal, what will happen? Because the current is flowing in this way, so the cathode of the diode is positive with respect to anode, so diode will not conduct. So, for this meter will not produce any, this diode output is 0. So, this meter will not produce any deflection. So, when next cycle will appear, then again it will produce a signal. So, this meter will measure the average value of this signal. But what is the drawback of this circuit? That this diode behavior is very non-linear. If we see the characteristic of this diode in positive characteristic, if we draw the input characteristic of this diode. So, when this voltage increases, then this is the linear region. So, this will follow the Ohm's law, but the lower portion of the diode current is not following the Ohm's law. So, it means this, because of this non-linear behavior of the diode, this meter will show not show a correct accurate value, but it will show some different value. So, we have to remove this non-linearity of the diode. So, for removing this non-linearity, because the forward resistance of diode is very low, so we have to increase this resistance, we have to place a series resistance whose value is very high, so that the resistance of this diode can be neglected. So, for this purpose we have to place a resistance over here, and whose value, this resistance value is suppose RS, the value of diode resistance is suppose RF. So, the value of this resistance should be very high with respect to RF, so that we can this the non-linear behavior of the diode will not affect the measurement. So, by placing a diode we can measure the average value of this current, because the diode is converting this AC signal into DC signal, then this meter will measure only the average value of the voltage. So, that is the average responding voltmeter. Then we can use this diode with a capacitor for the measurement of the peak value of the signal voltage. So, these two, average responding and peak responding, these two type of voltmeters are used for the periodic signal, that is periodic in nature. It may be of any shape, but it should be periodic in nature. But if any signal that is not periodic in nature, then that signal can be measured by the RMS responding voltmeter, that is true RMS meter. So, if we are having any signal that is triangular signal, rectangular signal or sinusoidal signal or any form of signal that is not in nature of the repetition, then we use RMS corresponding meter. So, this is average responding voltmeter. So, in average responding voltmeter, we can see we are using previously I told you that if the diode behavior, we want the non-linearity of diode will not affect the response of this PMMC instrument, then we have to use a very high value of resistance. Again, if we are using a high value of resistance, what is the problem? There is I square R loss, and that will create heat effect, and that because of this heat effect the diode behavior will also change. So, it will again affect the performance of the meter. So, in place of resistance we are using electronic devices. So, there are so many electronic devices, like we can use transistor, we can use FET, MOSFET. Here we are using operational amplifier. So, what is the characteristic of operational amplifier? Ideally we are considering an operational amplifier is having very high, ideally it is having infinite input resistance and 0 output resistance, but practically it offers very high input resistance, that is approximately 10 mega ohm. So, here if we want to measure, so we are using an op amp. So, operational amplifier, this input signal is applied to the operational amplifier, and then this amplifier is in the configuration of this voltage follower mode, or we can say it in buffer mode. So, a negative feedback is applied, we can see the negative feedback is applied and the input is applied at the non-inverting terminal. So, due to the negative feedback, this op amp provide very high stability, and due to negative feedback its input resistance increases and output resistance decreases. That is why we are using operational amplifier here. Now, the output of operational amplifier, when we apply input at the non-inverting terminal, then and we provide a feedback to the inverting terminal, then this op amp will try to make the same voltage at this inverting terminal. So, it means ki when E is the input voltage, then it also try to make E voltage at the inverting terminal. It means this V output of this is equivalent to E input voltage. So, E voltage is here and then it is deflected by the voltmeter, but there is a diode. Diode converts AC signal into DC signal, but what is the problem in this? That there is a drop of diode across diode, that is Vd. So, we know that if generally we are using silicon diode, so the diode has a voltage drop of 0.7 volt. So, it has a 0.7 volt drop. So, if input voltage is E, so the voltage after this diode, that is the Vm voltage will be E minus, Vm voltage will be E minus 0.7 volt. So, it means whatever the EM voltage we have applied, the meter, the voltage across meter will appear, that voltage is 0.7 volt less than the emitter, this input voltage. So, that is the drawback, and if suppose we want to measure the input voltage of 1 volt, then the voltage that appears across the meter will be 0.3 volt. So, the first thing is that it will have a drop of 0.7 volt. Second thing, we can't measure the voltage whose amplitude is less than 0.7 volt, because this diode will not conduct. So, to remove this this problem of this circuit, we have to take precision rectifier. So, precision rectifier is a special type of rectifier in which this op amp and diode combination is available in IC form, and we can use it. In this precision rectifier, what will happen? This operational amplifier and diode is connected in series, and this negative feedback is applied after the diode. So, it means ki whatever voltage drop is because of diode, that will not affect the measurement. Why? Because the input voltage is E volt, means at non-inverting terminal the voltage is E volt. This op amp is trying to keep its inverting terminal is also at same potential. It means if E volt is here, this output is also equivalent to E volt. So, it means the meter will show the VM meter, the voltage meter, the same voltage that is applied at the input, that is appeared across the this meter, PMMC meter, and so PMMC meter will show the exact value. This amplifier we are using, but here we have not used the attenuator, we have not used the amplifier. So, this meter is not this is a single range meter, and we can't use it as a multi-range voltmeter. So, for using multi-range voltmeter, we have to use a resistance, these resistance, that is here R1, R2, R3, R4, as I have already discussed in last lecture, that we can suppose this meter is having the maximum voltage that we can apply across this meter is 1 volt. So, this because of this range selector or this combination of attenuator will not provide more than that voltage. So, and here for when we want to measure an AC signal, then we have to block the DC signal, DC voltage, if any DC voltage is in the signal. So, suppose we have applied input here, we are using a blocking capacitor. So, function of this capacitor, as we know that the capacitor reactance increases as its frequency decreases. So, for the DC voltage, the capacitance, the reactance of the capacitance is infinite. So, it will not pass any DC signal. So, it will only pass the AC signal. So, AC signal is passed through the blocking capacitor, then there are resistance. So, by this whatever the range we want to select, we will place the selection switch at that point, and that will give the particular voltage value. Then we have used an operational amplifier. Yes, we have applied this input to the non-inverting terminal of the amplifier, and we are providing negative, means negative feedback to the signal to this op amp. The advantage of the negative feedback is that it provides stability, it increases input resistance of the operational amplifier, it decreases output resistance of the amplifier, it also increases the bandwidth of the amplifier. So, this and here because we are not using any resistance, so basically we are feedbacking the output to the input. So, there is no amplification factor of this op amp. So, here if the input is applied, suppose this type of sinusoidal signal is applied. So, when this positive cycle appears, the op amp will pass that positive signal over here, and then that current will flow through this diode. Suppose this is D1 and this is D2. So, it will flow through diode D1, then meter, PMMC meter, then this capacitor, and then it is fed to the negative terminal of the op amp, means it is a negative feedback system. So, in this amplifier, basically this average responding voltmeter is basically passing both the negative and positive cycle of the signal. So, during the negative half cycle, suppose this cycle will appear. So, the current will flow through this meter from here and this way and this way, the circuit is completed. So, these two capacitances are basically used as a filter, and again it will block the DC component if any DC component is available there. So, it will both the voltmeter previously discussed, or this is the multi-range voltmeter, and it is the full waveform, that was the half wave rectifier, this is the full wave rectifier. So, full wave rectifier also gives the average value of the signal. Suppose we want to measure the RMS value of the voltage, then we have to calibrate this scale of this PMMC meter in RMS value. So, it will also display the RMS value of the voltage. Similarly, suppose we want to measure the peak of any signal. We do not want to measure the average value or the RMS value of a voltage, we want to measure peak value of the voltage. Then we will place a capacitor over here. So, the input signal that we want to measure, this is the input signal, this is the input signal. Okay, so, this is suppose V input. So, it is applied through a diode D and there is a capacitor. So, what will happen when the positive half cycle of this signal will appear, then this diode will conduct, because diode only conduct when anode is positive with respect to cathode. So, this diode will conduct, and when this diode will conduct, this capacitor will charge with the peak value of the input signal. So, suppose this is the input signal. So, what will happen when this positive half cycle is passed through the diode, then this capacitor will charge to the maximum value, and after that when negative cycle appears, because the diode negative cycle means this direction of current will flow. So, here the cathode of the diode is positive with respect to anode, so diode will not conduct. So, when diode will not conduct means there is no discharging or charging of the capacitor. So, the capacitor will keep that voltage across it, the Vc voltage, it will maintain, the capacitor will maintain that value. To maintain this value, we have to that the RC time constant of this capacitor and diode, R is the diode resistance and C is the capacitance value. So, this RC time constant of this combination should be much greater than the time period of the signal, so that this capacitor is charged till the next cycle will appear. If it is less than this, then capacitor start discharging through the diode in the negative during the negative cycle. So, the value of RC should be very high with the time period of this input signal which we are applying. So, this at once this capacitor will charge, it will keep store that value of the voltage across it and it will not discharge. So, you can see in the discharge in the charging cycle, the diode it is offering 0.7 volt voltage drop and this capacitor is charged. Practically this voltage, the V input is less than 0.7 volt is appearing across the capacitor, but ideally if we consider that diode is ideal, it is not offering any resistance, any voltage drop, then it is this capacitor will charge with the full voltage. And discharging period, this diode will act as an open circuit. So, there is no circuit completed. So, capacitor will not discharge. This capacitor can discharge with the DC amplifier, but since the charging time of this RC time constant is very high, the capacitor will not discharge. Then we are using AC amplifier. If the signal amplitude is very low, then we have to amplify that signal and it is fed to the meter. If the signal amplitude is already very high, then we have to use attenuator to decrease the amplitude of the signal. Then RMS responding voltmeter, if we want to measure the RMS value of the signal, AC signal. So, for the RMS value of AC signal for the measurement, what we can see, we can use a heater circuit. We can use a heater circuit and AC current is flowing through this heater and then heater will produce a heat, and that heat that is produced by the heater is proportional to the V RMS square. So, this heater is getting heated up when we use a thermocouple. If we place this heater and a thermocouple in close proximity, then what will happen? This is suppose the thermocouple, there is no connection between these two. So, this is thermocouple and this is heater. So, if we heat up a heater by any voltage whose RMS value we want to measure, then this heat, because of this heater, this thermocouple will produce a voltage. Thermocouple is basically as we know, it is a transducer which converts which converts the temperature, change in temperature into change in voltage, or you can say the thermal energy into electrical signal. So, thermocouple is made up of two dissimilar wire, and at the junction if a temperature is applied because of two dissimilar wires, this will produce a potential difference. So, this concept is used in true RMS voltmeter. So, in true RMS voltmeter, here the input voltage is applied, we input across this heater, then heater will heat up, and then this thermocouple will produce a voltage across its two wires. Suppose it is two wire, it is producing a voltage E across this. So, this voltage E is proportional to the V input RMS of V input V RMS square, that is the RMS value of the V input signal. So, this the proportionality constant E is equal to K into V RMS square. This K is a constant whose value depends upon the material of thermocouple and the heater and the distance between these two. So, if the distance between these two are more, then this K is less. When they are placed very close, then the this K will be high. So, this concept is used, but what is the problem with this? We can place a meter here, PMMC meter, and that meter can detect the value of E. But what is the problem in this? That this thermocouple will have a very non-linear characteristic. So, this non-linearity can affect the measurement of this voltage. So, what we have done? We have to place two thermocouples in a chamber, same chamber, so that if there is any change due to the environment, their behavior change. So, the effect of one thermocouple is cancelled by the second thermocouple. So, we can see here the AC the unknown signal whose voltage we want to measure, whose RMS voltage we want to measure is applied at the AC amplifier. Then there is a heater circuit and the thermocouple is placed over here, then that is signal is amplified by the DC amplifier because it is converted into DC signal, and now DC amplifier is producing the voltage E here, and that E voltage is equivalent to the V input voltage, RMS value of the V input voltage. Then this voltage is negatively fed back to the second thermocouple. So, what will happen, and these two thermocouples are in bridge in form of the bridge. So, whatever there is any difference, that will be cancelled out. So, if due to change in environment or due to any other conditional change, if that will affect the performance of the thermocouple, then both the thermocouple will compensate each other's performance, and the PMMC meter will show the RMS value that is equivalent to the. So, this meter will show the V RMS value of this input voltage. So, similarly, we can measure current, because we are also we can measure the current with the electronics instrument. So, for the current measurement, we know the PMMC in electronic circuit, the current is measured when voltage is applied at a constant resistance. So, here this RS is a constant resistance and this is the emitter terminal. So, suppose we want to measure the current in this current in any meter. So, we will place an emitter here. So, the current is flowing through this resistance RS. So, the voltage drop will produce across it, and that voltage difference is measured by the instrument. So, RS is constant, V is equal to, we know V is equal to RS into, suppose the current I is flowing here. So, I, it means V is equal to RS into I, since RS is constant. So, RS is constant means V is proportional to I. So, that voltage is applied, this E voltage is proportional to the current. So, this voltage is applied at the operational amplifier. In this operational amplifier there is a meter is placed, and this meter is showing the current. This meter will show the voltage that is proportional to the current. So, in this way we can measure the current of the voltmeter. We can measure the current by using the voltmeter. So, this is the current measurement instrument. So, now we can use these are all are the analog measurement devices. So, analog signal can be measured, and the display is also in the form of analog. So, we can use multimeter to measure this signal in the digital form. So, multimeters are again of two types, one is analog multimeter and other is digital multimeter. And through multimeter we can measure AC voltage, DC voltage, AC current, DC current and resistance. So, in this lecture we have discussed the analog meters, analog voltmeters that are used for the AC measurement signal. In next lecture I will discuss the digital multimeter, how the digital multimeter perform, how it produces the output. That is all. Thank you from my side.